Hello again. This is Math 2245 coming to you from the College of DuPage. And the title of this lecture is Linear Programming Part 2. And it includes an embedded low-stakes assessment, yet another low-stakes assessment. As always, please be attentive while watching this video. By way of introduction, previously there was a part 1 where we talked about how you do this conceptually and in 2 dimensions. Herein we talk about the simplex method, which can solve much larger problems, and hereafter we make reference to some additional enhancements that can be made to this study of linear programming. In fact, there are entire courses that are taught in linear programming. So there's much to learn, and some of you may be interested in those elements. But this is what we're going to do first. We're going to talk about the simplex method, and we're going to address a problem where we're maximizing the objective function. And so we'll learn how to write the simplex tableau for linear programming. We'll talk about pivoting to find an improved solution. And we'll talk about how the simplex method works to solve a linear programming problem, at least whenever we're maximizing an objective function. And we will do examples where we have a real-world word problem, and we'll use a simplex method to find the optimal solution. So as we begin our discussion of the simplex tableau, the graphical method that we talked about in the earlier video is convenient and conceptually talks about what's going on. But for problems involving more than 2 variables or a large number of constraints, it's better to use methods that are adaptable technology, and we will talk about that here. And one very important such method is called the simplex method that was developed by George Dantzig in 1946. It provides a systematic way of examining the vertices of a feasible region to determine the optimal value of the objective function. I am going to tell you one last George Dantzig story. When he was trying to demonstrate that this works at the Rand Corporation, he solved a toy problem dealing with 9 nutritional elements, and he created a optimal diet for this. His wife had interest in diets at the time. And so they spent several days actually coming up with the solution to this by hand, because they hadn't programmed the simplex method yet. And when they came up with the optimal solution, he showed it to his wife, who declared that it may be optimal, but it is boring. Here is a picture of George Dantzig receiving a technology Medal of Honor from Gerald Ford, who was then the president. Okay, so back away from George Dantzig then. So say you want to find the maximum value of an objective function, z equal 4x1 plus 6x2. Those are the decision variables, and they have to be non-negative, so you do have non-negative constraints as well, but we have the additional constraints that are given here as inequalities. Now the left-hand side of each inequality is less than or equal to the right-hand side, so what we're going to do, and what George Dantzig did, because for the most part we deal with solving equations, not inequalities, he introduced non-negative numbers S1, S2, and S3 that are being added to the left side, so turning these into equalities rather than inequalities, and those are going to be called slack variables. And so here you see I've added S1, S2, S3, and now I've changed those into equalities. And again, those are called slack variables because they represent the slack in each inequality. And this is what we're going to call a linear program in standard form, where the objective is to be maximized, not minimized. And you can solve the other kind, we're just not talking about it now. And here also in standard form, all the inequalities are originally facing this way, so I'm adding slack variables in this way to get equations. So anyway, this is, for this discussion, the standard form of a linear programming problem. We will discuss that you can deviate from this, in particular when you're using technology. Now, we define a basic solution of a linear programming problem in standard form is a solution where we have values for the x variables, but also for the slack variables, and at most m of these are non-zero. And the variables that are non-zero are called basic variables. And what we are going to do is we're going to evolve our basic variables as we go through the simplex method to find the optimal solution. A basic solution for which all variables are non-negative is called a basic feasible solution. So the simplex method is carried out by performing elementary row operations. You've seen those before, haven't you? On a matrix that is called the simplex tableau. This tableau consists of the augmented matrix, again, you've talked about those before, corresponding to the constraint equations together with the equation of the objective function. But the objective function is now written in this form. Instead of z equaling all these things, you put everything on one side. So you have, this is now equal to 0 at the outset of the problem. So this is minus c1 x1 minus c2 x2 minus dot 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 minus cn xn plus. There is a 0 value associated with each of the slack variables, and then we move we've moved those things. Instead of z equal all that, we moved everything on the side with z. So on the tableau, it's customary to omit the coefficient of z, so there's a 1 there, but a lot of times you don't write it. And so now what we're going to do is we're going to look at the simplex tableau for linear programming problem. So you see that z is our objective function, and we are looking to maximize this in a standard form. But down here what I have is this is the 0, and I don't write z here usually, although you could. It really doesn't matter. Some books will tell you to write it, others will not. But you see the coefficients here is I'm getting these are on the same side. So the coefficient of x1 is -4. And the coefficient of x2 is -6. And then what I do is I write the coefficients for these equalities. So here I have -1 x1 plus x2 plus s1 is equal to 11. Here's the right-hand side. And then I have x1 plus x2 plus this is s2 is equal to 27. And then I have 2x1 plus 5x2 plus s3 is equal to 90. Now, what happens here is we start with the basic variables being the slack variables. Now, we don't expect these to be involved in the final solution, but this is where we start. So you see we have 1, 1, 1 here. So this means we're starting with s1 being 11, S2 being 27, and S3 being 90, and these others are 0. And this is our so-called initial tableau. And notice, please, my dear students, that except for the non-negativity constraints, what happens is we have everything is represented in this tableau, this augmented matrix. Okay, and so there you go again. So there are the basic variables are S1, S2, S3, and the non-basic variables at this stage are X1 and X2. Now note that the basic variables are labeled over here, so we do keep track of that, and that's important because you proceed through the simplex method. You have to keep track of what is in the basis and what is not. What is your basic variable? Okay, so we start with X1 and X2 as non-basic variables, so they have initial value of 0, and the current value of z is also 0. It is right here. And I already said we have these values for your non-basic variables. So the current is this. Now this is a basic feasible solution, and it could be written in a vector form like this. And again, the entry in the lower right-hand corner of the simplex tableau is the current value of z. And note that the bottom row under x1 and x2 are the negatives of the coefficient of x1 and x2 in the objective function. Okay, now this is something new then. To perform an optimality check to see are we finished yet for a solution represented in the simplex tableau, you look at the entries in the bottom row of the tableau. If any of these entries are negative, and it is here, then the current solution is not optimal and we have to proceed to the next step. But now we're going to talk about how do we go to the next step. How do we decide which basic variable enters the solution and which basic variable it leaves the solution? Okay, so here is what goes on then, and this is called pivoting. It doesn't surprise you that it is. The entering variable corresponds to the least, and the least in this case will be the most negative entry in the bottom row of the tableau, excluding the right-hand side column. So we're going to look across the bottom and we say what basic variable enters, and that's going to be the one that in this case is the most negative, but that will cause the greatest increase in the objective function. The departing variable corresponds to the least non-negative ratio. This is BI over AIJ in the column determined by the entering variable. And whenever this, and the only time this is going to be happening is when AIJ is greater than 0, because otherwise that will be negative. The entry in the simplex tableau in the entering variables column and the departing variable is how we will pivot. We will pivot to bring the entering variable into the pivot by eliminating the departing variable. That's why we call it pivoting. And finally, to form the improved solution, we are using Gauss-Jordan elimination to do this, and this is what we call pivoting. Okay, so let's do this. To find an improved solution, this is the LP that we were talking about before. And so you see this is the initial tableau that we have. Now when we look down here, we're going to see that the most negative thing, and we do have negative numbers, that means this isn't as good as we can do, and we're going to take this -6 to be the pivoting column, because that's the most negative number. So you see that means that x2 is going to be entering, but now we have to look and we have to decide which one of these basic variables is going to be leaving, and that's going to tell us our pivot element. Here we have our pivot column, and we have to figure out which one, S1, S2, or S3, is going to be departing. Okay, so we compute these ratios. So you see here, this is going to be 11 over 1, because that number was 1. This number is going to be 27 over 1, because there's the 27 and there's the 1. And this is going to be 90 over 5. We had those numbers from our pivot column. And so you see, we will take the least non-negative ratio, which if you look at those, you say, oh, that is going to be 11. And so we choose S1 as our departing variable. And that means we're going to be pivoting here. And what we're going to be doing is we're going to be getting rid of S1, and that means that we're going to have this entering. So let's talk about how we do that pivot then. Okay, so before pivoting, we have this, but we use these elementary row operations, and again, the one that we want to get rid of is the S1, so that's going to be how we're going to do it. And so before pivoting, we have this, but after pivoting, what you see is now we have a new tableau that's shown here, and the new tableau has that x1 is now a pivot variable. It's part of our basic solution, and we see that S1 is no longer that, because this is not 1, 0, 0. I've removed it from there. So this x2 now is in the basic solution. So x2 has replaced S1 in the basic variables column, and this is the improved solution. And notice that the solution is improved because now my value for z is not what it was before. Now it is going to be, and you see the solution up here is x1 is 11, and so 6 times 11 is 66. So I improved the value. Now in the event of a tie, when you're choosing the entering or departing variable, you can choose any one of the tied variables and it will work out. Now we're still not optimal, because if we look at the bottom row, there's still a -10 there. And so what I'm going to do is I'm going to be looking at this column, and I'm working to enter x1 into the solution. And when I start looking at the ratios I'm looking at And in this case, it's going to be 16 over 2 is 8. And this one is 35 over 7, which is 5. And so this time S3 leaves, and this is how I eliminate S3. And again, what I'm doing is pivoting to bring x1 into the entering variable. And notice that when I complete the pivot, and here's the pivot operations, I have that there's a 1 in the x1 column, and that's only 1. So that is a pivot. That is in the basic solution, and there's a 1 here. So now I have x1 and x2 in the solution. And this is the new simplex tableau. Now notice that I'm not really finished yet with the problem, because what I have to do is I have to bring in S1 because it is still negative. And so the entering variable is going to be S1, and the departing variable is going to be S2 in this case. And notice that S2 is still part of the basic solution here. So I do that, finish the iteration, and notice that things change now. And so now I have across my bottom row, after the pivot, 0, 0, 0. All these are positive, and I have a value of 132, excuse me. And that is the maximum value, and this means I found the optimal solution. And here is a graphical schematic, how you can see how you trace through that, and notice that you always were increasing with each step through the process of the simplex algorithm. The value, we went from z equals 0 to z equals 68 to z equal 116 to z equal 132, and now we are finished because all of those are positive. So to summarize the simplex method then, you convert each inequality in the set of constraints to an equation by adding slack variables. You create the initial tableau. You locate the most negative entry in the bottom row, and that gives you your entering column. And then you form the ratios of the entries in the B column with the corresponding positive entries in the entering column. If all of them are 0 or negative, there's no maximum value. The departing row then corresponds to the least negative ratio, BI over AIJ. And for ties, you can go either way. And the entry in the departing row and the entering column is called the pivot, and that's where you pivot. And then you use elementary row operations to change that pivot element to 1, and all the other entries get changed to 0. And that process in this algorithm is called pivoting. When all the entries in the bottom row are 0 or positive, it's your final tableau, and you're finished, and you know the solution. And you have, in this case, a maximum value, and you know the values of the variables. We have 2 more examples we'll talk about, but this time we're using 3 decision variables. You should pause and make sure you follow these calculations. So here's our problem. Notice now we have 3 variables and we have these constraints. And notice the non-negativity constraints are explicitly listed here. Okay, and so we add slack variables and we set up our initial tableau, and this is our initial tableau. So you see we have negative values, so that means that x3 in this case is going to be entering the basic solution. And we have to figure out what is departing, and we find out that S1 is departing here. And so then we perform the pivot, and you see the pivot is we're getting X3. This is going to be 0, 0, 1 in this case, because we do that pivot, and we make all those others 0, and so this is what we have. And if we look across the bottom, we see that there are no negatives, so we're really done. We found the optimal solution. It's going to be this 15 here, and you notice that you still have a slack variable. It's 20, but the only value that we have for our basic solutions is we have that x1 then is 5, and x3 is 5 over 2, and those add up to 15. Now, occasionally, the constraints in a linear programming problem will include an equation, And in this case, the slack variable is called an artificial variable, and technically it's not a slack variable. And so once you've determined an optimal solution to such a problem, check that the equations in the original constraint are satisfied. And example 3 illustrates such a case. So here we have the problem. Here's our objective function. Subject to these constraints, you notice that one of these is an equality, and this is x1, x2, and x3 are all non-negative. Okay, so here is your initial tableau. You see we're not optimal yet, and so we will be having x1 enter, and we will choose to depart on s1 because it's the minimum value. So we perform that pivot. That means we change the x1 column to 1, 0, 0. And that is good. And now we look across the bottom once we've done that. And notice you do the pivoting down here as well. You do those calculations on all of them. But now we have still have a negative down here. So we're going to be entering with this. And so that means that x2 is going to be entering. And when we do the minimum ratio rule, we see that S2 is going to be departing. So we're pivoting, and we're pivoting to make this a 1. So this becomes 0, 1, 0, 0 there. And so we've had that enter. And again, S2 departs. And so at this stage of the game, what we have is and we've found the optimal solution already to this. And so the optimal solution is going to be that this is going to be 3, 18, and x3 is 0. And the slack variable does have a value, but it doesn't contribute to that. And it turns out that this solution satisfies the equation provided in the constraints, checked here, and so it is an optimal. Now, there are many commercially available optimization software packages that help researchers do this. And I'm going to point you at Solver. Many of these do use the simplex method, as Solver does. And so you can solve big problems this way, and you can, check solutions and so on and so forth. And in addition to optimizing the objective function, these packages contain built-in sensitivity analysis and so forth. And so they're actually very powerful and Now, we are not going to go into modifications to the simplex method to do minimization, although it's some nice mathematics. It talks about the dual of a linear programming problem, which involves work by the great John von Neumann, but we're not really going to deal with that here. And also we can have mixed constraints of equality and greater than and so on and so forth, including we can insist that we have integer values here. But the online tools will do all of this for you, and so we're not going to dive into here. We're going to focus in class on other things. But I am going to be asking you to solve a problem, and this talks about using Excel, and the tool that you use here is going to be Solver, and this reference talks about that. And here's the LSA I'm proposing you for. So a manufacturer produces 3 types of plastic fixtures, and the table shows the times required for molding, trimming, and packaging. These are the 3 industrial processes. Times are in hours per dozen fixtures, and the profits are dollars per dozen for the fixture. Okay, so this shows you what happens for type A, type B, and type C, both the profits and the time required for manufacturing. So the maximum amounts of production and the time that these are listed below. And you see these are constraints. These are going to be your right-hand side. So you have 12,000 hours for molding. You have 4,600 hours for trimming, and you have 2,400 hours for packaging. So the question is, how many dozen units of each type of fixture should they manufacture to get the maximum profit? I'm asking you to do several things. Number one, formulate this as a linear programming problem. That has to be done. And once you formulate it as a linear programming problem, solve it by hand using the simplex method. Again, there's 3 variables, and so this is going to some work. Then I'm going to ask you to solve it using Solver, which is available in Excel, which is free to College of DuPage students. And then I'm going to ask you to submit documentation of all elements of this problem. And Jesse Hayes Carver will figure out when this is due. He'll also figure out if this is one LSA or perhaps multiple LSAs. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself, because self-care is important. And now more than ever, take care of each other, because we're all in this together. God bless you all, and look forward to seeing you in class.